Thank you all for joining us for the inaugural Texas FIRST Robotics Competition workshop, hosted by FIRST RGV. A little bit about us, and then we will turn it over to our presenters today. FIRST RGV is a nonprofit founded in 2015 that supports the FIRST community in the Rio Grande Valley, which is an area approximately 3 hours long by 2 hours wide, sits next to the border of Mexico. Yes, in Texas, it's easier to measure by driving hours than miles, just because Texas is just large. Since 2015, we have seen explosive growth of teams in our FIRST LEGO League and FIRST Tech Challenge program, but our growth in the FIRST Robotics Competition program is positive, but we are not where we need to be on ensuring access to the more than 250,000 students in the K through 12 space here in the Valley. With our events like this, we are doing our part to create awareness of our efforts and the need for strong sponsors and mentors to help our community. We are proud Texans, and I'm honored to be part of the FIRST in Texas Robotics Territory. Our organization is proud to be hosting this weekend's event. If we have any technical issues, please remain patient. We will get them resolved as quickly as possible. While you're engaging in the chat, asking questions, and saying hi to your neighboring team, or maybe a team across Texas, we ask that you remain on topic and know that this session is being recorded for teams to take advantage of this great information later. We will post this information on the FIRST RGV YouTube channel, and you can access it directly by visiting youtube.firstrgv.org or by searching for FIRST RGV on YouTube. I want to personally thank the FIRST Robotics Competition teams across Texas that have come together this weekend to make this live event possible, and for the hard work of our FIRST senior mentors and AmeriCorps Vistas across Texas that stand ready to help support our teams. On behalf of FIRST RGV, we hope everyone has remained safe during this pandemic, and we are confident that all of the partners across Texas will be getting ready to bring you a robotics season soon. Thank you.
Hi, I'm Jacob Henderson from 2468, and I'll be presenting on simulations and their implementation in LabVIEW. So before we start getting into the code part, I wanted to go over some basic things you should know before getting into simulations. So the first thing you should know is that simulations function on a very basic use of calculus, namely derivatives and integrals. So before implementing or attempting to implement a simulation, you should have a very basic understanding of how to use these and how they equate to finding new equations that you can use. Simulations themselves are primarily used to find variables that you're looking for. So torque, RPM, voltage, current, these are all things that simulations would be helpful finding, because they're things that would affect subsystems, and that's what simulations would definitely be used for. So graphs are what we use to output these simulations and get what their outputs are, because otherwise we wouldn't be able to see what they're actually giving us, and they'd be essentially useless. And these graphs help us to fine-tune our specific inputs so we can hone in on the correct set of variables so we can get the outputs that we want. So to start, I wanted to go over this voltage equation, and this is basically the starting line. This voltage equation equates the voltage of a motor to a certain speed and velocity. So the voltage equation itself is voltage is equal to IR, which is current times resistance, plus omega divided by a voltage constant. And that's basically all for that slide. So in terms of applying this to a robot, obviously robots can be broken up into different subsystems, and depending on what robot you're building and what game you're building for, subsystems will be different. For infinite recharge, we had a shooter, intake, dry base, and a hang. And we decided that the shooter would probably be the easiest thing to build a simulation for. But if you're going to build a simulation for a different subsystem, you're going to want to figure out the control mode for each motor in the subsystem. So the flywheel motor for the shooter is looking for an angular velocity, as we want to know how fast it's rotating. And then an elevator per se would be looking for a linear position because we want to know how quickly it's rising and falling. And it's important to have an understanding of physics and math so you can easily change between these two types of control modes, and you can understand like what type of equations would go to which type. So going more into the derivation side of things, like I mentioned before, that voltage equation is going to be the initial starting point. It's where we get all the equations that we use in simulations. And you can't just use the voltage equation itself. You actually have to derive it and get different equations with different variables in order to find a more apt and succinct way to find the variables you're looking for. So it can be a little bit difficult to find the derivation that you're looking for. So what we end up doing is finding the equation that we want, maybe online or something, and then plugging variables in to get it to more exact more exactly to what we want. Getting into the implementation in LabVIEW, we have our take on the subsystem and how it's implemented in a simulation. So we decided, like I said before, to take a relatively easy subsystem, like a shooter with a flywheel. And this is because it's a simple subsystem, because it only has two motors, both are spinning a flywheel, and it's a very simple way to calculate angular velocity, torque, current. It's definitely not too difficult in that regard. And simulations are important. I actually wanted to just point this out because our flywheel during season last year, we actually couldn't quite hone in on the values that we wanted for it. We ended up manufacturing 3 separate flywheels, each with different radiuses and weight and widths, just because we didn't know what we needed. And so during, at the end of season, we decided to try to implement the simulation because we realized that it'd be much more effective and easier to use rather than just manufacturing more and more things and wasting more and more parts and time. So getting into the actual equation that we're going to be using for this flywheel, we have in the bottom right there, click, there's that equation. And that's the derivation of the initial voltage formula that we were talking about before. And so there we're looking for final angular acceleration using a bunch of different constants and variables like gear ratio and moment of inertia. It's not entirely important to understand exactly what that equation is and how it works. It's just important to know that that's the equation we're using. So on the far left there, you'll actually see a group of inputs. And then these inputs are basically everything that you're going to need for the subsystem. The user inputs them, obviously, and it contains things like motor type, breaker amperage, the initial RPM of the motor, battery characterization, flywheel coefficients, gear ratio, etc. And then those values are going to be plugged in to a lot of different areas in the simulation, which causes them to be very important. And knowing how to use them is also an incredibly important thing to do. So if we head into the one of the input VIs, we'll see that you have a cluster or 2 clusters on the far left. And both of those serve to give you information regarding the motor. Now, the motor you can change as one of the inputs, and you plug it in to this sub VI, and that gives you the different motor values. So you get things like stall torque, stall current, free speed current, and you get the mass, radius, and coefficient of the motor. And these things are very helpful for finding things like the physical values of the motor, the free speed, the motor coefficients, and the motor model values, which we'll see as output on the far right. I think you'll have to click a bunch here because there's a couple of animations that we skipped. So if you click again, you'll see that we're looking at the M1 and M2 blocks. And then these VIs are helpful to combine torque and current, because as the values that are being inputted aren't graphable, we need to change them into something that is graphable. And so that's what those VIs are doing. And if we actually head into those, we'll see some of the math that's involved in that. So it's not actually too much complicated math. It's mostly just some basic division, subtraction, multiplication, etc. And you use that to find the current, motor torque, and power of the motor. So you're able to send that to a graph and see how it changes in regards to the different inputs you're going to give it. So if we look towards more of the center, we'll actually see a VI that's called the motor coefficients VI. And this VI is used to calculate the angular velocity and the flywheel torque given the motor values that we set as input. And so if we head into that VI too, we'll actually see just a lot of simple math again. We take the gear ratio and we multiply it by the motor torque and then divide that by J, the moment of inertia, and we end up with angular acceleration and the flywheel torque, which are two very important values that we need a lot in the equation that I showed you guys before. So as a whole overview, you'll see there's a lot of VIs that I didn't really explain in much depth. Many of them are self-explanatory or not very useful in terms of like actually implementing a simulation. Some of them are just testing or fail safes. So a lot of the things I did want to go over are the more important and definitely the more valuable topics to understand and learn about when talking about simulations. So if we look at the far left, click, yeah, we'll see a bunch of the different inputs. And these inputs obviously correspond to the inputs that are shown in the block diagram in the coding part. And, and these inputs are very important because they change a lot of the different values we're going to get based on, the gear ratio, the moment of inertia, the initial RPM, the breaker amperage, all that stuff. It's very important because it's going to change a lot of the values we get, and it's going to affect how we read our data. And in the middle, we'll see the graphs that I was talking about earlier. And these graphs are obviously important because they serve as the output and basically the only method we have of understanding the numbers we input and how they affect the numbers we get out. And at the bottom, there's a little slider. It's the VBus slider. And if you don't know what percent VBus is, it's essentially just the power percentage that the motor is given. So 100 is fully forward, negative 100 fully backwards. And sliding that up and down while the motor is moving actually shows you how much of a current load that gives the motor and how much of a current load that it takes on the battery. And that can cause a lot of brownouts or issues, and understanding that and being able to check for that is a very important thing. And that's also quite helpful for simulations.
Hey, I'm Christian Fueling on 2468, and this is my presentation on our path planner. All right, so wait. First, I'll mention what a path planner does. So it basically gets a bot from point A to point B with any number of intermediate points. And ideally, you want to have an optimal path. Now, what this means is it's two main factors: is the speed, how your bot takes to travel the path, and then when it comes to wheeled robots, there's smoothness. It's important because you don't want to damage mechanisms by being too jerky or tipping the bot. And this slide right here is the main UI of our path planner. So in this whole gray area, the field image, you can select points and that'll make the path. This field is just taken from the game manual. We just put the image in here, and we have a configuration file that maps the pixels to real world values. On the right, we have this palette for commands because our paths, they have commands stored within them. And then when we run the path, it'll just the commands will automatically get called. So you don't have to like run a part of a path, stop, call a command and then run another path. So it just makes the code a lot cleaner. Here, the user can set various conditions for the path, such as initial velocity, final velocity, and then limits on velocity, acceleration, and jerk. and then other things like selection override. And to the left of that is just the list of all the path files. Down at the bottom, we have a velocity curve along with it has the duration of the path and the distance it travels. And if you hit the green play button, it'll like show the red arrow on the field move along the velocity curve. So now I'll talk about how we generate the curves for our points. So the main thing we use is an Euler spiral, also known as a clothoid. So each waypoint is represented as an XY pair, and theta, which is a navigation angle. And so in the diagram, theta B is the navigation angle for point B. And so what we do is we generate a clothoid from point A, and it goes up until the point X1, Y1, and then we cut it off and mirror it. So it's the same curve going in and out. And theta B is defined as the following in the slide. So while developing the path planner, we thought it'd be useful to make a plotter for Euler spirals. So this is it. As you can see in the top right, there's a little key for the things. Okay, is a little key for the various visuals. So on the sliders on the top left, T is kind of represents the length of the Euler spiral. If you increase it, the curve would go longer. Truth. Yeah, so as you can see, it's a longer curve. And also you can do increased scale magnitude, which just literally scales it up bigger. And also down below, there's many variables relating to the things discussed in the last slide. So now I'll talk about how we, the velocity of our path. So to make our path smoother, we try to run at a constant velocity, except for when we're accelerating and decelerating at the beginning of and the end of paths respectively. As you can see here on the left is one path at 4 feet per second, and as you see, it gets pretty close to the intermediate point. And on the right, we have the same path but at 6 feet per second. And to maintain constant velocity, we can't get as close to the point as the 4 foot per second one. Additionally, our path planner has visual marks on the path to show various things. So the green line on the beginning of the path is acceleration. The gray just means we're driving straight at a constant velocity. Blue means we're turning at a constant velocity, and then orange is decelerating. It's not, can you go back, Drew? It's not very optimal for speed to use a constant velocity because we have to end up driving more distance anyways. But with a 15-second auto, we've never had issues with time. Since our curves are represented as mathematical functions and are continuous, it's not very friendly to store on a file or in memory when you're running the path. So we need to make it a more memory-friendly format. So what we do is we sample where the bot will be every 20 milliseconds. This is configurable, but we usually just run with 20 milliseconds. As you can see on the graph on the right, as the bot's moving slower, the points are closer together, and as the bot increases in speed, the points get farther apart. So we also use the path planner to tune PID for our drive base. What we do is we make a squarish path like this, and we just run it in a loop. And this is good because we can tune turning and distance and make sure that the bot will end up in the point. And we can get refined tuned by driving this over and over and seeing how error accumulates over time. Now I'll talk about how we drive the actual path. So for a small period of t, the bot will move f units forward. To account for driving in a curve, it needs to move some f minus d ticks per second on the left, or millisecond and ticks per millisecond on the right, or f plus d on the right. And d is defined as w times tan theta. Theta is the navigation angle. As you can see on the second diagram, it's actually just the same triangle, but rotated 90 degrees. And so d represents basically how much farther one side will travel than the other. And one thing I forgot to mention is we then divide d by time to get the motor speed we need to set. All right, so this file is called calculate velocity set points. It's located in the play path section, which is the command we use in the K structure of the drive controller. And this does is it takes in the subsystem data and it outputs a left and right set point along with some other things. So first we index the current velocity and angle based off the iteration of the loop we're in. We also take into account whether the path is reversed or not. So if it's reversed, we just index from the opposite side of the array or arrays. This file confusing adjustment just uses the IMU with PID to adjust steering if we overshoot or undershoot. And right above it is a file called commands, which will call the current command if there is one. All right, so this code I kind of just zoomed in is what we just is basically the math in the last slide. So it takes in a theta and then scales it to time and then turns into a dv. Now the 1.4 is referred to as a, if you can hit it once, it's like a fudge factor, or really just treat it as an F term that we have to tune every year. Does it have a mathematical derivation? Maybe. We never took time to figure out what it really means. We just kind of tune this every year, and it works pretty well. Up at the top, we have code to adjust for how the difference, how off 20 milliseconds you are, because the points in the path are supposed to be every n milliseconds or 20 milliseconds apart. So if our loop runs at, say, even 18 milliseconds or 22, that's a 10% difference, which will mess up a lot of things in the path. And at the bottom, there's a file that just takes the dv and turns it into encoder ticks per millisecond. Now let's talk more about our LabVIEW specifics for the implementation. So this is the code that writes our path to a file. So first takes in the path or the directory where we'll store this file. And then takes in a file version, because we've had multiple versions of this path file throughout the years. So it's just, it's useful for when we reread from the file. Then we have path conditions. These are the conditions the user set in the UI, such as velocity, acceleration, jerk limits, and initial and final velocity. Next, these are user-defined points, which is just x, y, and navigation angle, which is theta. And then this is the main path data, which we use to drive the bot. It has all the it has the sampled points, so the x, y, and theta for that, and it has velocity for all of it. And additionally, it has an acceleration index and a deceleration index, which is basically where the bot, the index of the point where the bot stops accelerating and starts decelerating respectively. Next, we just have the time and distance the path travels. And lastly, this is all the data we need to call the commands for the path. So this is the autonomous setup we use. This is robot main VI. We have two important files in here that we use for auto. So the first is auto setup. This handles network tables and the selection of our autonomous. Next is auto runner, which just basically sends the play path command. So this is auto setup. So in the red box, this just takes all the paths on the RoboRio and lists it on our custom dashboard. Then this takes in the selection and it sends that path to a global, the auto global, and then we also display that path on the dashboard. This is the auto runner VI, which simply just takes in the auto global and just plays it. This is the play path command. So what it does is it takes in the path and then it uses get data, which simply just reads from the file. So yeah, it just chains read operations to get out the data we need. And then we have to operate on it to make it fit with the command data. So now I'll talk about the shortcomings of our path planner. It's really difficult to use multiple velocities. The whole idea is centered on having a constant velocity. So if we ever needed to not use that, it'd be a really difficult process. Also, it relies on precise timing, right? Having 20 millisecond intervals, or else the path will get messed up. And the last one was more of a consideration, is that we could use PWM motor controllers over CAN. So the main advantages would be it'd be cheaper. So we handle encoder values and PID on the Rio. Now the main problem is we lose all of the Spark Max libraries. So that's why it's more of a consideration than a shortcoming. But the idea was it could save money.
Hi, my name is Unnati Perry.
My name is Abhinav Perry, and we're going to talk to you about homography. So homography is the relationship between two planes, and each plane, or the idea is that we have points on each plane, and some of these points are actually corresponding, so they represent the same information. So the idea is to use homography to relate these points between the planes. So each point will have like an XY coordinate, and we will take these coordinates and represent them using homogeneous format. You don't need to know about that. It's just another way of representing a two-dimensional coordinate. And then we're going to multiply it by this homography matrix, which is the 3x3 matrix. And then that will give us the corresponding points on the other plane. Now, this homography matrix can actually be solved if you know 4 of the point correspondences on the different planes. And if you can solve that, you can use homography or the homography matrix in many different applications. And that is, homography matrix can be decomposed into pose information if you know the intrinsics about the camera. So that means that you can get information about the orientation of the camera or even the translation of the camera, and you can use this for various applications. So the homography is derived from the pinhole camera model. And basically what this says is that it's a mathematical representation of a camera. So the idea is that it has certain parts, such as like a focal point or a focal length. And all of these things combine so that way you can project 3D points onto the image plane. So yeah, some key things that you need to know. The focal point is the point that's bolded in the 3D coordinates or the 3D axes. Then the focal length is the distance between the focal point and the image plane, which is that gray rectangle. And then the image plane is actually where 3D points get projected onto. So when you're actually taking an image, that image plane is basically the image. Then you have your principal point, which is basically where it's CXCY, and that's basically a coordinate that represents the center of the image plane. Then you also have your optical axis, which is where your principal point and your focal point lie on. So then the idea of the pinhole camera model is that you have some 3D point Q, which gets projected onto the image plane at some UV, and then that is basically the pixel location of that coordinate. So if you do this for the entire environment, then you can actually get the entire image or what the camera is seeing. And this can all be mathematically represented on the equation to the right. So it's basically saying that you have a 3D coordinate XYZ, you're multiplying it by 2 different matrices, which we'll talk about later, and then you get UV1, which is your actual pixel coordinate on your image plane.
So transformation matrices are functions that change vectors, and vectors are just 2 numbers in a list. Transformation matrices store the basis vectors that determine the transformation, and the matrices on the left reflect vectors on the x and y axis. So Euler angles are a readable way to represent the rotation matrix, which is basically a transformation matrix but in 3D space. Rotation matrices rotate 3D vectors in 3D space. The columns have to be unit vectors, and they also have to be perpendicular to each other. They're stored as a 3x3 matrix, so multiply the rotation matrix by vector to rotate the vector. Pitch, yaw, and roll are the rotation angles about the principal axis, and they're stored within the rotation matrix, but you can use different representations for Euler angles.
So then before we were talking about the pinhole camera model, and there were two special matrices that we glossed over. And these are actually camera matrices. So a camera will have two different matrices that describe different aspects of the camera. So in this case, it's the intrinsic matrix and the extrinsic matrix. The intrinsic matrix is K, which is being highlighted over there. And what it represents is a lot of intrinsic information about the camera. So things like principal point, which is CX and CY, and then it represents the focal length of the camera. Now, if you notice, there's two different focal lengths, FX and FY. And the reason for that is that it's measuring the focal length in terms of pixel units. So, but the reason that it's different is that since pixels are not always square, they have a different width and height. So that way, if you measure the focal length using pixels, you're going to get different measures of pixels if you use the width or the height. So that's why you have two different focal lengths. And this intrinsic matrix, if you multiply it by a 3D coordinate in the camera space, then you're actually going to get the projection of that 3D coordinate onto the image plane. Now, the extrinsic matrix stores information such as the pose and location of the camera. And if you notice, there's actually a rotation matrix and a translation vector that are concatenated together. And basically what those represent is that is the rotation or orientation of the camera in space, as well as its position in space. So the rotation matrix will store the orientation, and the translation vector will actually store the position of the camera in space. And the reason that we multiplied this by the original 3D coordinate is because our original 3D coordinate is not given to us in camera coordinates. It's not given to us relative to the camera center or the focal point. It's actually given to us relative to another origin, which is somewhere in the 3D world. So by using the extrinsic matrix, we can convert the 3D points in the real world coordinates into camera coordinates. And then from there, we can use the intrinsic matrix to actually convert those camera coordinates onto the image plane. So that's the basis of the pinhole camera model. So some applications of homography are how you can use or you can decompose the homography matrix into pose information. And if you know the location of your camera in 3D space, if it's attached to some rigid body, like such as a robot, you will actually know the location of the robot on the field. So if you can track something like a vision target and apply homography, you'll have a very good estimate of pose. And this can be used in a variety of situations, such as like auto align, or you can shoot from anywhere if you know like your location, right? That's something that's pertinent to this game. You can also improve path planners because they require knowledge of your location on the field. So that's another really good use for FRC. As for the implementation, the rough idea is to use some vision target like the image shown. And the idea is to look at certain features and track them. So remember how we said that homography was a relationship between points on different planes? Well, now we're going to utilize this relationship. So basically, we have one plane, which is the image plane, and some of the features, you might think of them as corners, right? These corners will be on those image planes, right? So we'll know the pixel coordinates of those corners. Then in real life, we actually know that this vision target lies on a solid surface, right? It's on another plane. So we can actually get some coordinates of the feature points or the corners in the real world. And that's another set of points. Now, if you can get 4 sets of points, then you can actually use the 4-point algorithm to figure out your homography matrix, which will tell you what is a transformation between your image plane and the real world. If you know that, you can actually decompose this homography matrix and get your pose estimate and use it for the uses that were mentioned before. So here is a mathematical proof for how homography is formed. There's a lot of matrix multiplication here, but really it's just a simplified version of the pinhole camera model. So if you look, we're just expanding the intrinsic and extrinsic matrix into their forms. And then what we're doing is that we're actually enforcing the planar relationship, because we said that homography is a relationship between the image plane and another plane, or just 2 different planes. In this case, it's the image plane and another real world plane. So here we're actually enforcing that all the points must lie on the Z plane in the real world. So that's why if you look at the coordinates, the Z values are actually 0. because we're enforcing that planar relationship. Then by laws of matrix multiplication, the extrinsic matrix simplifies down, and we actually get this homography matrix, or this 3x3 matrix, which basically represents this entire transformation.
So once we have this homography matrix, we can decompose it into a translation and a rotation of the camera. So the definition of the homography matrix is the first equation at the top. And all this stuff is the proof and the matrix multiplication. But the main point is that the pose matrix gives you your rotation and your translation.
So then we're going to talk about the 4-point algorithm. At first glance, this looks very, very scary. It has a lot of matrices and a lot of columns, and it does not look very user-friendly. But you don't need to know any of this for the implementation. All you really need to know is the coefficient matrix, and you need to know the actual formula to use with the coefficient matrix. And basically, the coefficient matrix is just a combination of all the point correspondences. So we have 4 sets of points that are basically representing the same information on the two different planes. So now we're going to take those coordinates, those XY coordinates, and we're going to format them in such a way that it looks sort of like this coefficient matrix. Now we're going to call that coefficient matrix A, and we're going to call this resulting vector B, and then there's a formula at the bottom that tells us how to derive our homography. That's a very simple overview of the 4-point algorithm. Then here is some LabVIEW code that shows our implementation. So here you can see that we load an image. In real life, we would actually take this from a camera feed. But for demonstration purpose and debugging purposes, for now, we're just using images that we already took. The first sub-VI that you see is just a feature tracking VI or sub-VI. And basically what it does is that it extracts those feature points that we're trying to track. And those are going to be one of our sets of points for the actual homography. And then later on, you can see that we have some deriving homography sub-VIs, and then where we actually figure out what the homography matrix is using the 4-point algorithm. And then we actually decompose the homography matrix that we get into pose and variables. So in this case, it would be rotation, translation, and then we actually simplify the rotation matrix into Euler angles for a more readable format.
So here we're constructing the coefficient matrix from the 4-point algorithm. Then we use the formula to get the homography matrix from the corresponding points. And here we're decomposing the rotation and the translation of the homography matrix using that formula that we discussed in the previous slide. And now we're using this formula to make the rotation matrix more readable and convert it into Euler angles.
Thank you everyone for listening, and if you have any questions, please ask in the YouTube chat.
All right, thank you for a great presentation. Will these videos be available to watch later? Yes, happy chicken. You can watch them later on the FIRST RGV YouTube channel. We're creating a playlist for FRC Workshop 2020. Anybody else have any questions? I know that was a lot. That was amazing. Any other questions? All right, I don't see any other questions coming in. So with that, team, we will go ahead and close out the session. We do appreciate you all doing this advanced deep dive into LabVIEW. It was very informative for sure. So with that, we're going to go ahead and close out, and we will be back online tomorrow for 10 a.m. So to see what the upcoming sessions will be, visit portal www.firstrgv.org, and it'll have a complete listing for tomorrow's sessions. Thank you all for joining us today. This concludes this session. If you're watching us live, please take the time to go back to YouTube and pick up our next session, or you can always visit our live page at firstrgv.me/live and pick up the next session there. We appreciate you watching and participating in today's session.